Good morning, dear students, and welcome back to our course. Basically, we are discussing various aspects related to network theory, and in the last lecture, we discussed in detail about the concept of three-phase circuit, and we conclude that suppose if we are dealing with three-phase circuit, basically we have two di- two different types of configuration in which we can connect a load. First one is called as star configuration and second one is called as delta configuration. In case of star, this type of configuration is also known as three phase four wire system, whereas delta is also known as three phase three wire system. In case of star configuration, basically we have three individual wires for three different phases like R, then Y, and then B, and there will be one more terminal which is available in case of star, and that is called as neutral. And for that, we need to connect one more wire. That's why this system is called as three-phase, four-wire system. But in case of delta, because we don't have neutral concept, that's why here we need to have only three phases, and for each phase we need to connect a separate wire. That's why this system is called as three-phase, three-wire system. And then we also discussed that what is going to be there, or what is the relationship between line parameter and phase parameter in case of star configuration, and what is the correlationship between line parameter and phase parameter in case of delta. So finally we conclude that in case of star configuration, the line current and phase current are going to be same, but in case of delta, line current is root 3 times of the phase current, and in case of star, line voltage is going to be root 3 times of phase voltage, whereas in case of delta, line voltage and phase voltage are nothing but same. So these are the fundamental aspect that we have discussed in the last lecture. And we also discussed that suppose if you have uh, say resistors and they are connected in star configuration, how to convert or how to find their equivalent representation in delta. For example, here we have resistor R1, R2 and say R3, and suppose if you want to find out its equivalent delta configuration like this. So here we have resistor, then here we have one more resistor, and then here we have one more resistor. So how to find out this? Suppose this is going to be terminal A, this is going to be terminal B, and this is going to be terminal C. So how to find the value of this resistor? Suppose this is say RA, this is say RB, and this is say RC. So what is the expression of RA, RB, RC in terms of R1, R2, R3? Or suppose if you have a delta representation for a system, how to find its equivalent star? So that is very important. So here suppose if you know R1, R2 and R3, that means if you know star configuration of a three-phase connected load and you want to find out its delta equivalent, that means if you want to find the value of Ra, so we can find that equation as Ra is going to be equal to R1 plus R2 plus product divided by opposite. So here I can write here as R1 plus R2 plus R1 into R2 whole divided by R3. This is very important. In the same way, suppose if you know the value of RA, RB and RC, that means if you know the delta equivalent representation of a three-phase connected load and your objective is to find its equivalent star configuration, that means you want to find out the value of say R1, so that we can find out like this. So R1 is connected at terminal number 1, or you can say terminal A. So here we can write the product of RA into RC whole divided by addition of all the resistance. So here we can write RA into RC whole divided by addition. So it is going to be like RA plus RB plus RC. So in this way we can have the flexibility to convert star into its equivalent delta, or you can say delta into its equivalent star configuration. So these points we have discussed in the last lecture, and finally we also conclude that how to draw the phasor diagram for a three-phase circuit. The thing is that all the three phases are 120-degree apart with respect to each other. That means if you take mm, on reference axis, say voltage across any phase, say R phase, so exactly 120-degree apart we have the voltage across Y phase, and exactly 120-degree apart we have the voltage across B phase. And then based on what kind of load we have connected, we need to take lag, lead, find out the value of voltages, and then uh, make a suitable conclusion that what is the relationship between the corresponding phase voltage with respect to its line voltage quantity. So all these points we have discussed in the last class, and today we are supposed to wind up our network theory portion. As I told you that network theory portion plays an important role as far as electrical and electronics communication engineering students are concerned, because this topic is common for both the domain, and that too they carry huge weightage. So we are on the verge of completing this particular portion. So today we will basically make a quick revision on resonance resonance circuit. What is resonance, and what are the different types of resonance circuits available in network theory, their application, their importance, and then we will discuss some basic fundamental aspect of two-port network. Two-port network. So these are the two topic that we need to cover in today's class. So basically, I'm going to revise or make a quick revision of these two topics, like what exactly resonance is, what are the different types of resonance circuits available in network theory, their fundamental mathematical equations in terms of frequency, in terms of current, and if possible we are also going to cover some graphical representations in case of series resonance circuit, and then we will switch to the last portion of the topic that deals with two-port network. Now let us first discuss what exactly resonance is. Now, see here, what is resonance? In case of network theory, resonance is defined as a phenomena where the effective impedance of the circuit is going to be equal to its equivalent resistance. Or we can also define this particular phenomena as resonance is a condition in network theory where the net reactance of the circuit is going to be zero. This is very important, because we know that impedance is nothing but a combination of two components. First one is called as resistance and second one is called as reactance. It may be inductive one, it may be capacitive one, or it may be a combination of inductive and capacitive. But ultimately impedance is nothing but a combination of resistance followed by its equivalent reactance. Now, what is resonance? Resonance is nothing but a condition where the effective impedance of the circuit is going to be equal to the resistance. That means the net reactance of the circuit is always going to be zero at resonance condition. This is very, very important. Now, based on in what philosophy we have connected our elements, whether we connect them in series or we connect them in parallel, depending upon that we have basically two different types of resonance circuit. First one is called as series resonance circuit, and second one is called as parallel resonance circuit. Now, what is series resonance circuit? It is nothing but a kind of circuit where the three fundamental elements of network theory or of any circuit theory or of any circuit, like resistor, then inductor, and then capacitor, all the three elements are connected in series configuration. So here we need to connect them in series. So this is in series with this, like this, and to this we need to provide some input excitation in the form of AC voltage source. Let us consider that for the moment this is going to be plus. So here we have R, here we have L, and here we have C, and the current is supposed to flow in the circuit like this. So this is very important. So in case of series circuit, Why it is series? Because resistor, inductor, and capacitors are connected in series configuration. That's what is called as a series circuit. Now let's try to find out what will be the effective impedance of this particular circuit. So effective impedance of the circuit is nothing but, like, I can rewrite this equation in terms of J operator. So R will remain R, but here this is going to be J X L, and this is going to be 1 upon J X C, or I can write this as J X L. I can write this as J. What is XL? It is nothing but omega into L. This is very important. In the same way, 1 upon JXE, I can write here as minus J whole divided by what is XE? XE is nothing but your, or I can write here as this, XE is going to be 1 upon omega C. Okay, so instead of taking that in picture, this is very important. Okay, so instead of writing this as minus jxc, let me make a correction over here. This is very important. Instead of writing this, this is very important, minus jxc, minus jxc. Okay, now at resonance condition, what will happen? The effective impedance of the circuit is going to be equal to the resistance of the circuit. That means here it is going to be minus jxe, or minus jxe is nothing but omega c. This is very important. Now at resonance condition, we know that the effective impedance of the circuit is going to be equal to its resistance. So I can write here as the effective impedance of a circuit for this case is going to be equals to Z, which is nothing but R plus J XL minus JXC, or I can write here as R plus, if you take J common, it is going to be equal to what? XL minus of XC. This is very important. This is going to be Z. Now what is resonance? At resonance condition, the value of Z is going to be equal to R, or I can say that at resonance the effective reactance of the circuit is going to be 0. That means we need to treat this imaginary portion as 0. So if you apply that logic, I can write here as XL minus XC is going to be equals to 0, or I can write here as XL is going to be equals to what? XC. Now suppose if you are interested to find out at what frequency of supply voltage this particular phenomena is going to occur, because once we have decided the value of R, L, and C, the value is almost going to be constant. But the ohmic opposition offered by inductor and capacitor, they depends on the frequency of supply voltage. Hence, we need to find out at what frequency this particular phenomena is going to be there, or it is going to happen. So what we need to do, we need to replace this XL as omega L, and we need to replace this XC as 1 upon omega C. This is very important. And once we have done with this, we can easily find out the value of omega at which this phenomena is going to occur. So if you multiply it by omega, I can write here as omega square into L is going to be equals to 1 by C, or I can write here as omega square equals to 1 upon L into C, or I can write this as omega is equals to 1 upon square root of L into C. So this is what the angular frequency at which resonance phenomena occur in case of series RLC circuit. This is very important. And the unit is radian per second. In the same way, we can find out this expression in terms of normal frequency, that means in hertz. So how to find out that? Now see, we know that omega is nothing but 2 pi f. So I can write this as 2 pi into f is going to be equals to 1 upon under root of LC. Or I can write this as f is going to be equals to 1 upon 2 pi square root of LC. This is very important. So this is what the frequency at which resonance phenomena occur in case of series RLC circuit, and this frequency is called as resonant frequency. This is in hertz and this is in radian per second. So in radian per second, the expression is 1 upon square root LC, and in hertz, the expression is 1 upon 2 pi square root LC. This is very, very important. Now, let us try to discuss what is the value of current flowing through the circuit at resonance condition. What is the expression for this I? Now, basically the expression for this I in this particular case is nothing but I is going to be equals to what? V divided by Z. Now, V divided by what is Z? Z is nothing but this. It is nothing but R plus J in bracket XL minus XC. Now I told you that at resonance condition this component is going to be 0. So I can write here as Z is equals to, or I equals to V divided by R. This is very important. This is the expression of current flowing through this RLC circuit at resonance condition. That's why it is indicated by symbol I naught. So I naught is going to be equals to V divided by R, because at resonance condition the effective impedance of the circuit is going to be equal to its equivalent resistance. This is very, very important. Now see here, at resonance condition, because the imaginary component of impedance is going to be 0, so I can say that at resonance condition the value of impedance is at its minimum possible value. That means Z is available at minimum possible value. Because Z is available at minimum possible value, now see here, which is nothing but capital R. So I can say that at series resonance condition, the value of current at its highest possible value, because the impedance is at minimum. Since the impedance is at minimum level, current has to be at maximum possible level. This is very important. That means in case of series resonance circuit, the effective impedance of the circuit is going to be equals to R, which is at minimum possible value. Hence, the current is going to be equals to what? V by R, which is at maximum possible value. So at series resonance circuit, the current flowing through the circuit is available at maximum possible value or highest possible value. This is very, very important. And what will be the power factor in case of series resonance circuit? Now see here, what is power factor? Power factor is simply the ratio of active power divided by apparent power. It is indicated by symbol cos phi. And in case of series resonance circuit, the power factor of the circuit is going to be equals to what? 1, which is nothing but unity. Why it is going to be unity? Because at resonance condition, the net reactance of the circuit is going to be 0. Hence, the impedance is exactly going to be equals to resistor. And in case of resistor, the voltage and current are exactly in phase with each other. Hence, the value of phi is going to be 0 and cos 0 is going to be equals to what? 1. That's why at resonance condition, because the impedance of the circuit is going to be equals to what? The resistance offered by the circuit only. Hence, at resonance condition, the power factor is always going to be equals to what? Unity, or it is going to be 1. This is very, very important. Now, let us try to find out what is the variation of that current with respect to frequency. Suppose if you're interested to find out the variation of current with respect to frequency, so here we need to take current on y-axis, and here we are going to take the frequency on the x-axis. Now, initially, when the frequency is low or it is below resonant frequency, the impedance of the circuit is not exactly going to be equals to what? R. and because impedance is at highest possible value, current is at lowest possible value. So it has to be at minimum condition. Now if you increase the value of frequency, it was found that at some particular value of frequency, which is nothing but resonant, the value of Z is going to be equals to what? R, which is at minimum possible value. Because the impedance is at minimum possible value, current has to be at maximum possible value. That means at resonant condition, suppose over here, say F naught, the value of current is at highest possible value, and this is going to be equals to what? I naught. And again, if you increase the value of frequency beyond this resonant value, again this Z is not going to be equals to R, because the condition, that is XL, is going to be equals to what? XC is violating. Now it is not going to be exactly the same. Then in that case, again, the impedance is not at the minimum possible value, and hence current has to be reduced. So the variation of current with respect to frequency is going to be like this. In this way, we are supposed to have the graph of current with respect to frequency, and the effective reactance of the circuit below resonant frequency. That means in this particular region, because here the value of XC is more than XL, so it is going to be capacitive. But after resonant frequency, because the value of XL is more than XC, the net reactance of the circuit is going to be inductive. This is very, very important. And at resonant frequency, the XL is going to be equals to what? XC. The net impedance is going to be what? R. This is very important. And because the impedance is available at minimum possible value, current has to be at highest possible value, which is nothing but I naught. So this is what the variation of current with respect to frequency in case of series resonance circuit. Now, series resonance circuit, sometimes also known as acceptor circuit, acceptor, acceptor, or acceptance circuit. Now, why? What is the reason behind this? The reason is very simple. See, from the graph, it is very clear that at resonance frequency, that is when F is going to be equals to what? F naught, Z is going to be equals to what? R, which is at minimum possible value. Hence, current, which is nothing but V divided by R, is at highest possible value. That means at resonance condition, at resonance frequency, this particular circuit is going to allow maximum value of current signals through it. It is going to accept maximum value of current flowing through the circuit. That's why this circuit is also called as acceptor circuit or acceptance circuit. This is very, very important. I hope this point is clear to everyone. So at series resonance condition, the value of impedance is at minimum possible value, hence the current is at highest possible value, and it is going to accept all kind of current signal when the value of F is going to be equals to F naught. Hence the circuit is called as acceptance circuit or acceptor circuit. This is very important. And I already told you that in case of a series resonance circuit, the value of power factor is going to be 1. That is nothing but unity. Now let us try to discuss the concept of half power frequency. Now suppose if you plot a line corresponding to the value of current as I naught by root 3. Sorry, I naught by root 2. Or I can write here as I naught by root 2. So it is 1 by root 2. So it is going to be equals to what? 0.7071 times I naught. So here we have the intersection of current with respect to frequency at this point and at this point. So this is going to be the first frequency F1, and this is going to be the second frequency, which is nothing but F2. Now this F1 and F2 are known as half power frequency. Now why it is called as half power frequency? So to understand this, first of all, we need to calculate what is the value of power consumed by this particular circuit at resonance condition. So we know that power we can write here as P is equals to what? I square into R. At resonance condition, I is nothing but I naught. So I can write here as I naught square into R. That this will be your equation number 1. So this is the value of power at resonance. That means this is the value of power at F naught. Now if you want to calculate the value of power at F1 or say F2, so power at F1 or F2 is nothing but, again it is going to be P, which is nothing but I square into R. Now what is the value of I at F1 or F2? So from graph it is very clear that the value of I at F1 or at F2, magnitude wise they are nothing but same, and that is nothing but I naught by root 2. So instead of writing I am going to write that as I naught by root 2, then whole square into R. If you solve this, I can write this as I naught square into R divided by 2. Now from equation 1, I can write this as I naught square into R is nothing but the power consumed by that particular circuit at resonance condition, which is nothing but say P naught. So I can write here as this is going to be P naught divided by 2. Now from this equation it is very clear that at these frequencies, that means at F1 and F2, the power consumed by the circuit is exactly going to be the half of the power consumed by the same circuit at resonance condition. That's why these frequencies are called as half power frequency. This is very important. And once you know the value of F1, F2, we can find out the value of bandwidth, which is nothing but the difference between F2 and F1. This is called as bandwidth. And once you know the value of bandwidth, we can find out the value of quality factor, which is nothing but Q, quality factor of the circuit. This is very, very important. So quality factor plays an important role in order to find out the quality of given inductor, or you can say given capacitor. And quality factor is normally defined as the ratio of reactance, or you can say inductive reactance, because we are trying to define this in terms of inductor. So it is going to be inductive reactance divided by the internal resistance of that particular inductor. So this is what the expression for quality factor. So it is going to be equals to, in case of inductor, the inductive reactance is going to be equals to what? XL, and its internal resistance, suppose it is defined by R. So it is going to be equals to XL by R, or we can write XL as omega L divided by R. So this is the expression for quality factor in case of inductor. In the same way, quality factor in case of capacitor, we can define as Q is going to be equals to what? Again, it will be the same. That means the reactance. Now, in this case, it is going to be capacitive reactance, CR, divided by, or you can write this as, instead of writing CR, because C is capacitance and R is going to be resistance. So we can define that as capacitive reactance, which is going to be equals to XC divided by internal resistance of the capacitor, which is going to be R. Now we know that X is nothing but 1 upon omega C. So I can write this equation as 1 upon omega CR. So this is the expression for quality factor in case of capacitor or capacitive reactance, and this is the expression for quality factor in case of inductive reactance. This is very important. So finally, what we conclude? We conclude that in case of series RLC circuit, the net impedance of circuit is going to be equals to what? R, which is at minimum possible value. Hence, the current at resonance is going to be equals to what? V by R, which is at maximum possible value. Then power factor circuit is going to be 1, which is nothing but unity. And then the concept of half power frequencies F1 and F2. So power at this condition is going to be equals to what? P naught by 2, or I can write here as I naught square into R divided by 2. This is very important. And then quality factor. Quality factor in case of series RLC circuit for inductor is going to be equals to what? Omega L divided by R, or in case of capacitor it is going to be equals to what? 1 upon omega CR. And series resonance condition is also known as acceptance circuit, or sometimes it is also called as voltage magnification circuit. Why it is called as voltage magnification circuit? Because at series resonance condition, because the value of current is at maximum, the same value of current is going to flow through your inductor and capacitor. Hence, the voltage across those quantities are going to be at highest possible value. That's why this circuit is also called as voltage magnification circuit. Magnification circuit. So these points are very important, and this you have to remember. In gate, uh, sometimes it was found that they ask straight away questions like, the circuit. They mention in the numerical that we have resistor this much, inductor this much, capacitor this much, and they have all the components are connected in series configuration. What tell me the value of frequency or resonance frequency in hertz where the resonance phenomenon is going to occur. So it is going to be f naught, which is 1 upon 2 pi under root of LC. Or it may possible that they may ask this in radian per second. So it is going to be equals to 1 upon square root LC. So these formulae you have to remember. Once you know this, then let's make a quick revision on parallel resonance circuit. What is parallel resonance circuit, and how to deal with that? Now, see here, in case of parallel resonance circuit, instead of connecting RLC in series, now we need to connect RLC in parallel. So here we have R, and then here we have L, and then here we have C, and now they are connected in parallel configuration like this. So this is going to be R, this is going to be L, and this is going to be C. And to this parallel combination, we need to connect a voltage of V, and to this we need to find out I. So this is going to be IR, this is going to be IL, and this is going to be what IC. And then we need to apply the same logic again at resonance, irrespective whether the components are connected in series configuration or they are connected in parallel configuration. The net impedance of the circuit is always going to be equals to its equivalent resistance. So if you apply that logic from phasor diagram, we can find out the effective impedance in case of parallel resonance circuit, and the value is going to be like Z is equals to L upon CR. This is very important. So in case of parallel resonance circuit, the value of effective impedance is going to be Z, which is L upon CR, and it is at maximum possible value. This is very important. In case of series resonance, the impedance is going to be at minimum possible value. But in this case, the impedance is going to be at highest possible value. Because the impedance is at highest possible value, the current available in the circuit during parallel resonance condition is going to be at minimum possible value. This is very important. There has to be exactly ulta relation. In series, impedance is minimum, hence current is maximum. But in case of parallel, impedance is maximum, hence current has to be minimum. Because at this frequency, now what is the frequency or resonant frequency in case of parallel resonance circuit? It is going to be equals to what? 1 upon 2 pi square root 1 upon LC, then minus, here we have one more component, which is nothing but R by L whole square. This is the expression for frequency in case of parallel resonance circuit. 1 upon 2 pi square root 1 upon LC minus R by L whole square. Or suppose if you are interested to find out this in terms of radian per second, so it is going to be equals to what? Square root of 1 upon LC minus R by L whole square. This is in radian per second, and this is in hertz. Now, at this resonant frequency, because the impedance is at maximum possible value, the current has to be at minimum possible value. This is very important. And because at resonant frequency current is at minimum possible value, it will allow only limited signal of current to pass through the circuit at resonance condition. That's why parallel resonance circuit is also called as rejector circuit. Why it is going to be called as rejector circuit? Because at this resonant frequency it is going to reject and maximum of the signal and allow to pass only limited version of current signals, and that's why this circuit is called as rejector circuit. This is very very important. And as far as power factor is concerned, in case of uh, parallel resonance circuit, again because the net impedance circuit is nothing but resistance, the power factor has to be one. That means voltage and current has to be in phase with each other. So Like in case of series, again in case of parallel, the power factor is again going to be the same. That is nothing but unity. But there is a twist. In case of parallel resonance circuit, the expression for quality factor is exactly ulta, or you can say inverse of the uh, quality factor in case of series. That means as far as inductors are concerned, in case of inductor, we know that this quality factor is nothing but omega L divided by R. So this is going to be equals to what? R divided by omega L. This is what the power factor for parallel resonance circuit as far as inductors are concerned. In the same way, here we have QP, which is nothing but quality factor in case of parallel is going to be equals to 1 upon QS. And as far as this uh, inductor sorry capacitor is concerned, so this is going to be equals to what? uh, 1 upon omega cr, because in case of series resonance circuit, the value of this quality factor as far as capacitance are concerned is nothing but 1 upon omega cr. So it is going to be 1 upon omega cr. So it is going to be equals to what? Omega cr. So this you have to remember. That means in case of parallel resonance circuit, the expression for quality factor is number one, R divided by omega L, which is the inverse of the quality factor in case of series resonance circuit, or we can write here as omega CR. This is very important. Omega into C into R. This you have to remember. So this is what the basic quick revision of what exactly series resonance circuit and what exactly parallel resonance circuit. The thing is that in case of series, the impedance is available at minimum, but in case of parallel, the impedance is available at maximum. Because here impedance is minimum, current is maximum. Here, because impedance is maximum, current is minimum. This circuit is called as acceptance circuit. This circuit is called as rejector circuit. Here, power factor is going to be 1. Again, here power factor is going to be 1. In case frequency is going to be equals to what? 1 upon 2 pi square root of LC. But here frequency is 1 upon 2 pi square root of 1 upon LC minus R by L whole square. This is very important. And then here quality factor is say omega L by R, but here it is going to be inverse, so it is going to be R by omega L. These points you have to remember. If you know this, it is very easy to solve numerical on resonance if they ask in gate. Now let us try to discuss the last topic of the course that deals with two-port network. Two-port network. Now what is this? Now let us bifurcate this entire structure into two terminology. First one is called as port. Now what is port? Port means pair of terminal. Pair of terminals. Terminals. So one pair of terminal means one port. And here because we are dealing with two port network, that means here we need to deal with two pair of terminals simultaneously. And in one pair we have two terminal, positive, negative. So a kind of network or a kind of structure where we are dealing with four terminals simultaneously. One pair of terminal means one port, another pair of terminal means one more port. So a kind of network or a kind of structure where we have two ports simultaneously, that's why this network is called as two port network or a two port circuit. Now let us try to have a general representation for two port network. So two port networks are going to be like this. So here we have a network. So on left hand side we are going to indicate this is going to be first terminal and this is going to be second terminal. Now pair of terminal indicate port, so this is going to be first port. So here let us consider that the voltage which we apply is V1, or which is available over here is V1. and the current flowing through the circuit is nothing but I1. This is very important. In the same way, here we have another pair of terminal which indicate one more port. So here we supposed to have a voltage of V2 and the current flowing through this particular terminal is I2. Now this is what the general representation for two-port network. Why it is called as two-port network? Because here we have two pair of terminals simultaneously. This is one pair of terminal. This is going to be one port. This portion is going to be port number one, port one, and this particular portion is going to be another pair of terminal, which is nothing but port two. That's why it is called as two-port network. Now, two-port network plays an important role. The main application of two-port network in electrical domain, as far as electrical domains are concerned, they play an important role for the representations of transmission line. So, as far as two-port networks are concerned, here basically we have four fundamental operating parameters. Two parameters from port 1 and two parameters from port 2. That means port 1 parameters are voltage and current. In the same way, port 2 parameters are again voltage and current. Now, depending upon these dependency and independency, we can have the flexibility to classify this two-port network into six fundamental domain. Now, what is the meaning of this? Now, see here. Suppose we consider the port 1 parameters like V1 and I1. In the same way, suppose we have considered port 2 operating parameters like V2 and I2. Now, depending upon in what sense out of these four parameter, which two parameter we have identified as a independent parameter, and we are trying to find out, or we are trying to define the remaining two parameter in terms of those independent parameter, we are having total six possible combinations or six possible sets of two-port network. What is the meaning of this? Now suppose if you take I1 and I2 as independent parameter, that means I1 I2 are initially known to us, and we are trying to find out V1 and V2 in terms of I1 and I2. So that type of configuration or that type of two-port networks are called as Z two-port network, or sometimes they are called as Z parameter. Z parameter, where Z indicate the impedance. Now suppose if you are interested to find out the equation of Z parameter or Z two-port network, so how we are going to write that? Now here I told you that I1 I2 are independent. That means their values are known to us, or we are first going to find I1 I2, and once you know the value of I1 I2, we are trying to find out the value of V1 and V2. So I can say that V1 V2 depends on I1 I2. So V1 V2 are dependent, I1 I2 are independent, and these kind of two-port networks are called as Z parameter two-port network or Z two-port network. So the expression for V1 V2 now we need to define in terms of I1 I2 by using this function, which is nothing but impedance. So I can write here as going to be equals to 1 plus Z2 into V2. In the same way, I can write this as V2 is going to be equals to what? Z21 into I1 plus Z22 into I2. Or suppose if you are interested to find out this in terms of matrix, so I can write here as V1 V2. This is going to be in matrix. That is going to be equals to what? Z11. Then here we are having Z12. This is going to be what? Z21. And this is going to be what? Z22. And then here we are having I1 followed by I2. So this is what the representation of Z parameter or Z two-port network. So here I1, I2 are independent, and we are trying to find out V1, V2 in terms of I1, I2. This is very important. So this is first possible condition where we have assumed that I1, I2 are going to be independent, and we are trying to find out V1, V2 in terms of I1, I2. It may possible that in some cases we may take V1, V2 as independent, and we are trying to find out I1 I2 in terms of V1 V2. So that type of two port networks are called as Y two port network or Y parameter, where Y indicate admittance. This is very important. Let us try to find out, or let us try to find out the mathematical equations for representing Y parameter in case of two port network. Let's try and tell me what is the answer for that. Now, have you tried for this? Okay. So, uh, in this case, our objective is V1, V2 are independent, and we are trying to find out the expression of I1, I2 in terms of V1, V2. So, I can write here as I1 is going to be equals to like y11 into v1 plus y12 into v2. In the same way, I can write here as I2 is going to be equals to what? Y21 into v1 plus y22 into v2. Or in matrix, I can write here as I1, I2 going to be equals to like y11, then y12, then y21, y22, and here we need to have v1 and v2 like this. Now from this it is very clear that this v1 and v2 are independent, and we are trying to find out or define this I1 I2 in terms of v1 v2. So here we have the relation factor in terms of admittance. That's why these parameters are called as y parameter. I hope this is clear to everyone. Now it may possible that uh, someone may take the parameters of y port as independent like this, and we are trying to find out the parameter of first port in terms of second port. That means here in this case v2 and I2, this is very important, v2 and I2 are independent, and we are trying to find out v1 I1 in terms of v2 and I2. So this type of parameters are called as A, B, C, D parameters. Now how to write the equation for that? So I'm writing that equation over here. So I can write here as v1 is going to be equals to what? A into v2 plus b into minus I2. Now this point you have to remember, minus I2. Why we have taken minus, that I'm going to tell you, but you have to remember that here while writing the expression for ABCD, here we need to take current as minus I2. In the same way, we can also define that I1 is going to be equals to what? C into V2 plus D into minus I2. Now why we have taken minus sign over here? Now see here, this ABCD parameters are basically used to represent transmission line modeling or transmission line modeling of a line in case of power system. And we know that in case of transmission line modeling, suppose we treat port 1 as a source, then in that case port 2 has to be a receiver, and because port 2 is receiver, the direction of current has to be in the outward direction. But the basic representation of two port network, we have taken the current flowing inside the network, just to indicate that in case of ABCD parameter representation, the current is moving in the outward direction with respect to the considered reference value, because they are exactly 180-degree phase shift over here. That's why we have to take this negative sign into picture. So by default, in general, in case of two port network, the current must be going to enter through port 2. But because ABCD parameters are used to represent transmission lines in case of power system, and in case of power system, the port 2 is normally treated as a receiving end, and because in that case the current is supposed to leave the network instead of entering the network, and that's why we need to take negative sign over here. This is very important. And then in matrix form, I can write this equation as V1 I1. This is going to be equals to like A, B, C, D, and here we need to have like V2 and then minus I2. This is very important. Now in this case, we have defined port 1 parameter in terms of port 2 parameter. That means we have defined V1 I1 in terms of V2 and I2. So this is called as ABCD parameter. Then again, it may possible that one may define by taking this V1 I1 as independent parameter, and we are trying to define this V2 I2 in terms of V1 I1. So this type of representations are called as inverse ABCD, or sometimes they are called as A dash, B dash, C dash and D dash two port network, or inverse ABCD parameter. Now what we need to do, now we are going to write the expression of V1 V2 in terms of V1 we are trying to write down the expression of V2 I2 in terms of V1 and I1. So how it is going to be like, so I'm directly writing that expression for matrices. So I'm writing here as V2 I2, because now in this case V2 I2 are dependent, and we are trying to define this V2 I2 in terms of V1 I1. So it is going to be like A dash, B dash, then C dash, D dash, and here we need to write this V1 and then minus of I1. Again, we need to apply the same logic. Now in this case, we have connected the source at terminal 2 and we have connected a load at terminal 1, and because we have connected a receiving end, or we have assumed that port 1 is going to act as a receiver, that's why the current has to be flow in the outward direction, because actual current has to be in inward. Just to make a sense of that, we need to take I1 as negative. The same logic which we have applied in the previous case, the same logic we need to apply in this case also. So this is what V2 I2, we defined that in terms of V1 I1. So this is another possible condition. Now these are four possible conditions. In first case, I1 I2 are independent, we are defining V1 V2 in terms of I1 I2, and that is called as Z. Then second case, V1 and V2 are independent and we are trying to find out I1 I2 in terms of V1 V2, that condition is called as Y. Then in third case, we assume that V2 I2 are independent and we are trying to find out V1 I1 in terms of V2 I2, that is called as ABCD. And in fourth case, we assume that V1 I1 are independent and we are trying to find out V2 I2 in terms of V1 I1. That will be the fourth case, that is called as inverse ABCD parameter. Then we also have two more conditions. It may possible that someone may take one parameter from uh, port 1 and another parameter from port 2. That means we are now clubbing the two parameters from two different domain, because we are going to take one parameter from port 1 and one parameter from port 2. That's why this type of combinations are called as hybrid combination or hybrid parameter. So now what we are going to do, we are going to take this combination. That means we are going to take V2 and I1 as independent, and we are trying to define V1 I2 in terms of V2 and I1. So this type of configurations are called as hybrid parameter. Why they are called as hybrid parameter, or you can say H parameter? Because basically we are mixing. We have taken one parameter from port 1 and one parameter from port 2, and we are trying to find out, suppose if you take this type of combinations, how it is going to be like. So we are basically we are mixing or hybridizing. That's why it is called as hybrid parameter. So in H parameter, I1 and V2 are independent, and we are trying to define V1 I2 in terms of I1 and V2. So I'm writing that equations over here in matrix form, or here. So I can write here as V1 and I2 is going to be equals to H11, then H12, H21, and then H22 is going to be equals to, here we need to take I1 and here we need to take V2. Now see here, from this it is very clear that we are defining V1 I2 in terms of I1 and V2. So we have taken one parameter from port 1, another parameter from port 2. See, one parameter from port 1, another parameter from port 2. That's why this configuration is called as hybrid parameter or H parameter. And the last combination, which is nothing but inverse hybrid, where we need to club the remaining pair. Which one? This one. That means now we are going to take V1 and I2, this V1 and I2 as independent, and we are trying to define this I1 V2 in terms of V1 and I2. That configuration is known as inverse H parameter, or sometimes that is also called as G parameter or G2 port network. Let me erase this. So that we can write that expression over here. This is very important. So in case of inverse H, or it is nothing but G, so V1 I2 are independent, and we are trying to find out I1 V2 in terms of V1 and I2. So I am writing here as I1, then here we need to take V2. This is going to be equals to inverse H, or you can take that as G. So G11, G12, then it is going to be what, G21, and here we need to take G22, and this is going to be equals to like V1 followed by I2. This is very important. Now here we have taken one parameter from port 2, another one is from port one parameter from port 1, and another one is from port 2. In the same way, this is from port 1 and this is from port 2. So we are defining I1 V2 in terms of V1 I2. So it is a combination of hybridization, and because it is inverse, that's why you may take this as inverse H parameter, or sometimes this is also called as G parameter. Now because here we have only 6 possible conditions, now no possible conditions are remaining, that's why we have only 6 different types of two-port network. The thing is that out of these 4 parameters, in any one of a two-port network, we need to take any two quantity as dependent and the remaining two quantities as independent, and we need to define the expression of that dependent quantity in terms of independent. So if you apply that logic, based on that we have only 6 possible types of two-port network, like Y, then Z, then ABCD, then inverse ABCD, H, and then we have G parameter. क्योंकि छठवीं पॉसिबल कंडीशन के बाद कुछ बचता ही नहीं है, that is the reason we have only 6 different types of two-port network. So this is the answer for that, why we have only 6 two-port network, because we have total 6 possible conditions. If you have 4 parameters in your hand, out of which 2 parameters from port 1, 2 parameters from port 2, and suppose you need to take that in each case any two quantity to be dependent and any two quantity to be independent. If you apply that logic, you have only 6 possible conditions, and for each condition we named those two-port network. Like if you take I1 I2 as independent, that condition is called as Z. If you take V1 V2 as independent, that condition is called as Y. If you take V2 I2 as independent, that condition is called ABCD. If you take V1 I1 as independent, that condition is called as inverse ABCD. If you take I1 V2 as independent, that condition is called as H. And if you take V1 I2 as independent, that condition is called as inverse H, or you can say G parameter. This is very important. And in gate, how this questions are going to be framed on two-port network. The thing is that network is given to us, and they may ask that find out the Z parameter equivalent of that particular network, or in some cases it may possible that they may ask any of the two-port network representation for that particular structure. The thing is that we need to solve that particular network by applying the concept of KVL KCL and try to find out these values like V1 V2 I1 I2. Once you know the value of V1 V2 I1 I2, then it is very easy for us to find out any of the two-port network representation. So to solve that particular numerical, again we need to apply the concept of KVL, KCL, mesh, then super mesh, node, node, or any other network theorem. So this is what the concept of two-port network is. And then one more concept that remaining, that is nothing but the concept of this reciprocity and symmetricity in case of two-port network. So let me quickly have a discussion on that. What is reciprocity, or you can say reciprocal network? And here we are going to write symmetry, symmetrical, symmetrical network. And what is called as reciprocal network? Now, what is reciprocal network? Uh, in network domain or in network theory, reciprocal means what? If the ratio of voltage at one port to the current at another port is going to be the same ratio if you change the position of voltage and current, even though the ratios will remain the same, then that type of networks are called as reciprocal network. And what is called as symmetrical network? Symmetrical means what? If we measure the impedance at one port, and if the value of that impedance is exactly going to be the impedance measured at another port, by remaining or by keeping the remaining ports at open circuited condition. So if you have that particular logic, then that type of networks are called as symmetrical network. So in reciprocal, what we need to do, we have to take the ratio of v by I at one port, and suppose if you interchange the position, and suppose again you calculate the ratio, that is v by I, at different condition, and in both are nothing but same, then it's called a reciprocal. And in symmetry, suppose if you measure the impedance at one port, uh, by keeping the remaining sources in the deactivated mode, and suppose if you are calculated the value of impedance at another port, again by keeping the other sources as deactivated, and if both the impedances are nothing but same, then that type of networks are called as symmetrical network. So there has to be a condition for reciprocity, and there has to be a condition for symmetry in case of all the six type of two port networks that we have just discussed. So let me write those conditions directly over here. Like, what is the condition for symmetricity in case of z parameter, then y parameter, then what is the condition for symmetricity in case of abcd parameter, then inverse abcd parameter, then we have h parameter, and then followed by g parameter. So the condition for symmetricity in case of z parameter is nothing but the value of z11, if it is going to be equals to what, z22, then that type of two port networks, if they are represented in z, are said to be symmetrical two port network. In the same way, the condition for symmetricity in case of y is nothing but y11 is going to be equals to what, y22. In the same way, condition for symmetry as far as abcds are concerned, this is like a is equals to what, d, and then for inverse it is going to be like a dash going to be equals to what, d dash. And for z, now here this is a twist, this you have to remember. Let me mark star over here. So the condition for symmetry in case of h parameter is like h11 into h22 minus h12 into h21, this is going to be equals to what, 1. So this is, you have to remember. Then again, condition for symmetricity in case of g parameter, so it is going to be like g11 into g22 minus g12 into g21, this is going to be equals to what, 1. So this you have to remember. These are some twisted formulae. So in case of z parameter, symmetricity formula is z11 z22 y y11 y22 abcd, a is equals to d, inverse abcd, a dash equals to d dash, and for g and h, this is what the formula. Now, suppose if you are dealing with Z type 2 port network, and you are interested to find out whether that particular network is reciprocal or not. So, what is the condition for reciprocity in case of Z parameter? So, in case of Z parameter, the condition for reciprocity is when Z12 is going to be equals to what, Z21, the network is said to be reciprocal. In the same way, condition for reciprocity in case of Y parameter is like Y12 is going to be equals to what, Y21. This is very important. And the condition for reciprocity in case of abcd parameter, so it is going to be like ad minus bc is going to be equals to what, 1. And then the condition for reciprocity or reciprocal in case of inverse ABCD, it is going to be like A dash D dash minus B dash C dash is going to be equals to what? 1. Now here for hybrid parameter, the condition for reciprocity is H12 is going to be equals to what? Minus times of H21. This is very important. And then condition for reciprocity in case of inverse H or G parameter is going to be like G12, this is going to be equals to minus G21. So these formulas directly you have to remember, and in gate based on this formula you may have a question like some network is given to you and your objective is to find whether that particular network is symmetrical or not, or whether that particular network is reciprocal or not. The thing is that first of all find out any two port representation of that particular network. Like you may go for Z, you may go for Y or ABCD or inverse ABCD or H or G, and then apply any one of the condition based on the kind of representations you are having with you. For example, if you know the Z equivalent of that particular network, apply this logic. Like if the value of Z12 is equals to Z21, the circuit is said to be reciprocal. And if the value of Z1 and Z22 are nothing but same, the circuit is said to be the symmetrical. So these formulas you have to remember, and based on this formula directly in gate questions were asked. So this is what the end of circuit theory course. In the next lecture onwards, we are going to start another portion or next course which I'm supposed to take in this particular class, that deals with the concept of control system. Again, that particular course is common for both electrical as well as electronics and communication engineering student. Thank you.